All right, I want to talk about an ant. And I do a little bit of research on this one to be as accurate as possible because I had some ant enthusiasts once in the class. And I looked up a reasonable mass for an ant. So I got 1.53 milligrams for an ant. I'll give that a mass in kilograms. So 1.53 milligrams is 1.53 times 10 to the power of negative 6 kilograms. A milligram is 1,000th of a gram. And we have to get it into kilograms, not grams. And we say that this ant is moving along, at least at first, with a velocity v1 of 0.0200 meters per second. Ant's moving along to the right. I think we're going to make right be positive and left be negative because it looks like this ant is walking along here. And so we'll leave that velocity as being positive. And v2, the ant slows down. Notice the dots are getting closer together. Slows down to 0.00700 meters per second, also to the right. And I love ants. They're so cool. I actually had some balsamic vinegar. It's got sort of a sweetness to it. Spill on my patio recently. We broke a bottle. I have to clean up the glass. But the ants found it. And I could see all these little tiny ants walking towards it and these big swelled up ants that were full of balsamic walking away from it. So I can just imagine that they're having a delicious feast somewhere around the property. One of my kids, I won't say which one, did happen to squish one of them, and yes, a lot of balsamic vinegar came out of one of those swelled ants. I mean, ants are just like these amazing creatures. I regret the loss of that ant, but I really see that my whole bottle of balsamic is not going to waste, even if it's not going on my salad. Anyway, this ant is slowing down over the course of 6.00 seconds. And so you might ask a question like, find the impulse of the ant. Now, my first instinct is to write J is equal to F times delta T, but I realize, like right off the bat, I don't know force, but I do know some other information here. And I know that although impulse and change of momentum isn't exactly the same thing, I know that they'll numerically end up giving me the same results. So I might, instead of saying force times delta T, I might do P2 minus P1, which would expand out to MV2 minus MV1. And I know the mass is a little bit ridiculously small here, but maybe realistic. Remember, we're moving along at 2 centimeters per second and 0.7 centimeters per second here, beginning and at the end respectively. But sub in our values, 1.53 times 10 to the power of negative 6 kilograms times V2, 0.007 meters per second, minus that same mass times 0.02 meters per second. We do a little bit of math, and you check to make sure that my numbers are right, but I end up getting negative 1.989 times 10 to the power of negative 8 kilogram meters per second. And notice the units, kilograms times meters per second. It's not beautiful, but that's the units. Now, if I had used force times time, if I'd had that information, you might have ended up getting Newton seconds. That's strange, but those guys end up being equivalent units. Remember, Newton seconds would be kilogram meter per second squared times seconds, and the seconds would cancel out. So it's still going to end up being equivalent to kilogram meters per second. The units are equivalent whether you come at this from an impulse or a change in momentum way of thinking. The units are going to work out to being kilogram meters per second. And I guess I could write this properly for a therefore statement. I'm not going to write the therefore statement just for lack of space, but 1.99 times 10 to the power of negative 8 kilogram meters per second. And since it's negative, to the left, based on our reference frame. Now, a follow-up question might be, what's the ant's braking force? And I'm talking about like car brakes. What's the force that slows this ant down, the braking force? And if I was going to tackle that, I might say J is equal to force times delta T. I've already calculated the change in momentum, which is numerically going to be the same value as the J value, so I can calculate the force here, get the force all by itself, J over delta T, sub in my values, 1.9, use my unrounded with the negative, 1.989 times 10 to the power of negative 8 kilogram meters per second, divided by the braking time was 6 seconds, the slowing down time. And again, check my numbers, make sure that I've got this right. I get negative 3.315 times 10 to the power of negative 9 newtons, or approximately, I could say 3.32 times 10 to the power of negative 9 newtons to the left. And if you're paying attention to prefixes, 10 to the power of negative 9 is nano, so that would be about 3.3 nanometers, or nanonewtons, which is a strange force unit, but I don't really use very often. But it is an ant after all, so it's not going to take a lot of force to slow it down. Now, a reasonable part C for this, which I'm not going to take to completion, but I can see that we definitely could, based on our givens, we could ask what's the acceleration of this ant. And here we've got enough kinematics information. We could solve, find the ant's acceleration. Now there's a couple of ways that we could come at this based on what we know at this point. We could use F equals ma, because we've already figured out the force and we know the mass is the ant's mass, so we could solve for acceleration this way. Remember, we've just calculated force in part B, we know the ant's mass, so we could do it this way. Or we could go back to our original kinematics information, we could say acceleration is equal to V2 minus V1 over delta T. Either way, we've got all the information, V2, V1, delta T. We could solve it by either of those methods. We're going to leave that at that. There is one more thing though, and I want to focus in on this picture here, because some people get hung up on momentum and impulse, or change in momentum and impulse having the same numerical values, and so why would we make a distinction? So I've got this little explain this situation that I want to draw your attention to. If this car comes to a stop, it could come to a stop in a couple of different ways, well, lots of different ways, but let's just examine two. I know that it's going to have a final momentum, mv2, minus an initial momentum, mv1, and if this car comes to a stop, then we all acknowledge that v2 value is going to be to a 0. So no matter what, the change in momentum is going to be the same value if it starts at this speed and comes to a stop over here. But if we have a branching scenario where this car could take this route and crash into a wall to come to a stop. If the car crashes into a wall to come to a stop, we acknowledge that it's going to experience a lot of force when it hits that wall, and it's going to come to a stop over a very small amount of time. That's a very small t, if you can't see that very well, very small time. Whereas if this same car comes to a stop, not by hitting a brick wall, but by smashing into a pile of raked leaves, it's going to come to a stop, yeah. But it's going to take a longer time to come to a stop than if it just hit a brick wall. And the amount of force that the car is going to experience as it comes to a stop over that longer time is a smaller force. And so yeah, while the change in momentum is going to be the same for each of those branching options, this car is going to experience more force over a small time. This one's going to experience less force over a big time. The impulse really matters, and it really matters in car accidents. And it doesn't have to just be about cars hitting leaves versus walls. Instead of leaves and walls, I could have had a person. It could have been a person in the car, and say, okay, if you don't have an airbag, you're going to smash into the dashboard. That's going to be a big force on your body over a small amount of time. If you do have an airbag, it's going to slow down. It's going to make your process of coming to a stop take more time. That'll mean that less force gets exerted on your body, and that's going to cause less trauma to you as a person. So there's a couple different ways we can come at this. And I wanted to make sure it was clear why we really care about the difference between change in momentum versus the concept of impulse, even though the numbers all work out to be the same thing.